We're going to move on to thiols and sulfides. A thiol is a sulfur-containing compound that looks a lot like an alcohol group, except there is a sulfur present instead. So an SH group is considered a thiol. When we name thiols, we end the name in thiol instead of -ol. So here we would have, this would be 3-methylbutanol. And this one would be 3-methyl-1-butane thiol. So the 1 tells us where the thiol group is, butane tells us there's 4 carbons. Thiols are also referred to as mercaptans. The SH group can be named as part of a side group rather than as part of the parent chain. If you have a thiol present while there's also an alcohol present, the alcohol will take precedence over the thiol. This would be called 3-mercapto 3-methyl-1-butanol. And the reason that they're called mercaptans comes from their ability to complex mercury. 2,3-dimercapto-1-propanol is used to treat mercury poisoning. Thiols are known for their very unpleasant odor. Skunks use thiols as a defense mechanism, and you may be aware of skunk smell. Those smells are often associated with thiols. Methane thiol is a smell that is added to natural gas, methane, so that gas leaks can be detected. So natural gas normally does not have a smell, but they add that methane thiol to it so that you know if there's a gas leak. Your nose is a very sensitive instrument and can detect these things. The hydrosulfide ion, or SH-, is a strong nucleophile and weak base. So we saw this as a nucleophile when we use NaSH in the SN2 reactions. So this one promotes SN2 reactions over elimination reactions because it is a strong nucleophile. If we have this reaction here with sodium thiol with bromide, this is going to do an SN2 reaction. This is our nucleophile, electrophile, SH. Again, nucleophile attacks the electrophile. We're going to invert the stereochemistry there, and we get the SH. Other reactions that can happen, the thiolate can attack Br2 to produce a disulfide. This will polarize itself. So we have this electrophile. This nucleophile can come back in here because there's more floating around. And you form the disulfide. That's another SN2 reaction. If you have 2 thiols together in the presence of sodium hydroxide and water with Br2, you can form the disulfide again. So the thiolate with bromine can form the disulfide, or you can have 2 thiols in the presence of base and bromine to form the disulfide. There's also sulfur analogs of ethers. These are called sulfides or thioether. And this one's a regular ether. And just like ethers could be named as a side group, this would be 1,1-dichloro, 4-methoxy, cyclohexane. So ethers are named by whatever substituent is coming off here. This is in a methoxy group. If it was 2 carbons, it would be ethoxy. This would be a methyl thio group. So this same thing with the thiol would be 1, 1 dichloro-4-methylthiocyclohexane. Sulfides are generally prepared using nucleophilic attack of the thiolate on an alkyl halide. So thiolate plus alkyl halide, nucleophile attacks electrophile, and we get R2 there, plus NaX. Once you form the thioether, we can do other reactions with it. You have another alkyl halide. This is referred to as an alkylation. This alkylation occurs a lot in DNA with different nucleophiles, and that is what can lead to DNA mutations. Once you have this alkylated DNA, you have a good electrophile because it's positively charged. This is the electrophilic carbon, and we have a nucleophile that enters the picture and attacks this electrophile, and that's a good leaving group. But we get the thiol ether back, plus the CH3 nucleophile. Other reactions that we can do with sulfides include oxidation. If you have an oxidizing agent, we can go from sulfoxide, where oxidizing here is the addition of oxygens. Sulfoxide to sulfone has the two sulfur double bond oxygens. If you want to get to the sulfoxide, we use sodium periodate. And that will get you methylphenyl sulfoxide. So there aren't too many reactions that you are required to know for thiols. What we will look at next are synthetic methods involving epoxides and thiols. If you have an epoxide, we can do a nucleophilic attack. Open the ring and have addition of a nucleophile plus the OH. We can also add an OH to here via an epoxide. We're able to add two functional groups at one time. In this example here, if you wanted to do this reaction, we'd have a nucleophile followed by water. So the nucleophile would attack at one of these sides, open up the ring to the O-, water would protonate that. In order to get this one, we'd have to go through the epoxide first. So we use MCPBA to form the epoxide, and then use sodium cyanide in order to do the nucleophilic attack here. One thing that you'll notice is that the nucleophilic attack happened at the less substituted site. So if that occurs, we know he needs to be under basic conditions. So we'd want to use NaCN to have the Cn- versus something like HCN, and that will bring the alcohol to the other side. If you're trying to do a series of reactions, we can do that as well using epoxide. If we have an alkyl halide and we have magnesium, that makes it the Grignard. We add our epoxide, and that's a symmetric one, so we don't have to worry about regiochemistry. So we get O, addition of R, minus, and then we add water, get a proton transfer, H. So that would be our product there. Or if you already have the Grignard, followed by water, and we protonate there. So we can change the carbon skeleton. So you can think about how we might do a synthesis such as this one. So we're adding carbons. This group is getting added here. So one thing that I noticed is that we're adding 2 carbons followed by an oxygen. And this to me usually tells me that there is an epoxide involved, or could be. So if I dissect that a little bit, this might be a Grignard plus an epoxide. This is the less substituted carbon, and this could be stuff that's coming off of the epoxide. We can go back to this structure here. There was no restrictions on carbon minimums or maximums. So if I want to do this synthesis in the forward direction, I will add magnesium to form the Grignard. Add the epoxide, followed by water. So this Grignard nucleophile is going to attack this side. This bond right here will break and form this O minus, and that water will protonate it. I'm going to check the carbons that I added. I have 1, 2, 3, 4. This is 1, 2. Alcohol is at 2, 3, 4, and there's a methyl at 3. So that is one way you can do that synthesis. Now we can look at a couple of these fill in the blank problems. This first one, we have an alcohol. It needs to be on the less substituted side because we're using BH3. So our alkene probably was this. We do an oxidation with the Jones reagent. That will get us the ketone. And here we're kind of having a couple blanks, so we need to go backwards from here to see what our reagents were. And if I look at the carbon skeleton versus this back here, this was from the original, and it looks like there was a Grignard that was used to form a new carbon bond here, which made the alcohol. My step just before this was the alcohol. So this would have had to have been the Grignard. And to add the Grignard, you can just take this group here. So we're adding 2 carbons. This is 1, 2, MgBr. So just to check there, 1, 2. This is 1. And then in order to form the ether here, we want to use sodium hydride. That will remove the H, which can then attack an alkyl halide. So 1, 2, 3. And then a Br. So that's how you can approach that problem. In this next one here, we want to look at MCPBA, which makes an epoxide from an alkene. So I need to have had an alkene there. If I have an epoxide here, there's an OH, and my carbon chain has 1, 2, 3, 4, 1, 2, 3, 4. I'm not actually gaining or losing carbons. We're just opening the epoxide on the less substituted side. And so usually this is going to be a source of H minus, so you can use lithium aluminum hydride here. If you add HCl at this tertiary, we can do an SN1 here. That would swap out the Cl with the OH. In this reaction here, this is our original carbon and alcohol. So we're adding an SCH3 at the less substituted. So we want a nucleophilic CH3SNA. We want a nucleophilic addition or basic addition. So this is going to the less substituted. This also went to the less substituted side. If your alcohol is on the more substituted carbon, that means that there was an attack or hug at the less substituted site. For the last problem, you can try to propose a synthesis here. This would be the original carbon chain with an oxygen. If we're working backwards, an epoxide needs to come from an alkene. So it might have looked like that. And to form an alkene, you might have something with a leaving group there. And maybe we had an OH here. And I only went through the OH because we can use Grignards. The other nice thing about Grignards is if you do a nucleophilic attack with a Grignard to a ketone, we still have a functional group there. And what I mean by that is if you had an acetylide, we added this, the functional group, once the acetylide attacked, is gone. We only have this handle over here. But with a Grignard, if you attack there, we have a functional group here that we can play with, which is what I'm trying to get to here. So before we got to this, we have MgBr plus that right there. So you can see this carbon and that oxygen there. So you can see the carbon. Okay, so the OH, carbon, that chain there came from that. Okay, so we can get to here from there. So I'll do that in this color. So first we need to change this OH to a Br. Use PBr3. Add magnesium. To propanone, to butanone. Add our ketone with water. So we have that. Then I want to do an elimination with the least substituted. So I'm going to make it a good leaving group first. So I'll just do PBr3 again. So I can do zinc chloride followed by T-butoxide. That gives me the double bond. And then I can use MCPBA. And that is how you would do that problem.